Hi there. Let me explain how the working of this MATLAB code. I have sent you a reference paper. Let me open that reference paper. So here is the reference paper. So I have sent you in a minute ago to your WhatsApp number. And optimal placement of DG tuning, consider power loss minimization and voltage stability enhancement in power system. So this paper is actually done by the genetic algorithm, and I took the formulation or constraints or fitness function from this paper, and then I have implemented the different optimization techniques. This paper was done by the genetic algorithm. So here is the further analysis, and I hope so you have checked the without dg file. In that file uh, I have tell many things how the load flow analysis is working. So here we have, this is the Jacobian matrix that I have mentioned there, how that Jacobian matrix works, and that theta and v is mentioned here. This is, and here the main problem is here, just from the line number 18 to 24. The system constraints are described in 18 to 24. So 18, here is the PD, and PGI equals to PL represent the load, system load, and PG is the uh, power generated or generation at a bus, and PDG is actually the power submitted by the distributed generation, and QDG is the power submitted, reactive power submitted by the DG at a specific line, and QL will deduct that specific reactive load from that piece. So here we have our DG real power constraints limits, that is 40% penetration set, and QGI is the penetration limitation set for the distributed generation reactive power. So here is a but you here is a load flow analysis, but sorry, flow chart, but nothing is clear from this. So many papers is doing similarly. So our main thing in the load flow of this paper is the Jacobian matrix, that is here at this point, and this is also the part of the Jacobian, also this one, and these are the mention in the, let me show you. Here is the MATLAB code that I sent to you, and let me open the feed power, and in the feed power here is the part where I have mentioned the different combination of the DG power size. So then what happened next? Here is the load flow for the calculation. So let me start how it's working is. So here is the ABC, that is main. So I name I the name of this file is just ABC, but hill function, simple hill climbing, is also involved in this case. So without DG case, when you watch the previous video, that will be covered. So let me left click here and start a debugger here. So let me click on the run button and click on the var size, that is the decision variables minimum, and lower bound, and n bus is the maximum. So n bus is here is 33 bus system, and we can install our distributed generation at any bus from 1 to 33. So maximum iteration and population, onlooker bees. So in ABC there are three type of bees. So here is the initialization, and here we have to set the power factor. Let me put 1 here. When I put 1 here, then it will be take only reactive power of the DG, and when I will put 0.6 here, then it will take 0.6 percentage of the real power of DG and 0.4 percentage of the reactive power of the DG. And when I put here 0, then it will take only reactive power of DG, and do not take power of dg as a real power. So let me go with the 0.6, both reactive and real injection, and let me uh, put debugger another here. Okay, and when I put 0.6 here and when I click on the okay, you want to I have updated the code again, so let me introduce the 4 digits. Okay, so let me click on the step button. When I click sorry so when I click on the step button, so now here is the algorithm starts. So when I click on the step button, here is the hill function. Now this line will be going to the hill function. Here is the hill function. Let me open this hill function. That hill function, let me move it here, and here we have calc here uh, actually h double l is the hill function output, and so actually what's that, uh, hill function is the file name, and start points is the inputs of this file, and that are 5, and h double l is our output. So now we are going to move here. Let me left click here and start debugger here. When I click on the step button, here is the uh, algorithm, you can say algorithm, or the working principle, how the simple hill climbing is working. So we have started this from the bits, 1 bit for the sign, plus minus 2 bits for the integer part, I mean where we have to put the integers, I mean 15 point or 17 point or 100 point. So do 2 bits for integer part and 10 bits for the decimal part. How much, I mean if we want to take 57.29. So let me just for any example 57.29, just for example. So 1 bit for the sign, this line will indicates minus or plus, and next line will indicate where we have to put the point here, or here where we have to put the point, and next is the 10 bits for the decimal part, so here is the 57. So here is the starting of the program, and just to get into the program we have set a small limits here. So here we are going to the my convert str. So let me open the my convert. Oh, actually program is going to closed. Let me again 0.75, let's put 4 and click on the run button, and when I click on the step, then here let's here is the my convert. There is one more file here. Let me open that file, my convert. Here is the my convert file, and let me click on the step button here. So from these lines we have sorry from these lines we have created a string here. Let me open the str here. Here is the str, and that are the 72 points that are selected randomly. Okay, so let me close this str, and now we are going to into my convert file. Str we have put, and we have outputs here. Str that I show you from here workspace. My convert is the file name where we are going to. Let me start a bugger here, and num1 num2 3 4 is our outputs. So let me click on the step button. Here we are going to. So str first value is our sign from 2 to 3. Let me click again str first. Str first will tell us the sign, and str 2 to 3, I mean second value, third value. Actually I have a recorder, and that recorder have just 10 minutes of to record a video. So let me here uh, from 2 to 3, this will represent the integer part, and from here from 14 to 18 we have a representation of decimal parts. So here is the binary to decimal conversion, and let me click on the button here, and when only click on the next button, let me remove this debugger. So here we have a num1, that is our output, and that is 28 119 422. So here is the next steps to calculate the star points and all these things. So my aim to explain all these things is actually when I click on the step button, let me drag it here and click on the continue button. So my explanation of local search was that to introduce HLL that we have taken from the hill function, and from hill function we have my convert function, and that was all things was randomly generated. So HLL, I mean local search, will represent our distributed generation locations. I mean here we have HLL, and HLL have four values: 11, 19, 14, 16. So it will these HLL function will represent the digi location, and we have four digi locations, and their locations can be randomly selected from 11, 19, 14, 16. So this is going to be stored here in the pop-I function, and next we have this function is for the distributed generation size. So here is the minimum value, that is 1, and maximum value is 33 for distributed generation size, and here is NVAR, that we are going to set the for distributed generation. So when I click on the step button, so now let me open the pop-I position, this variable. So here is in the workspace, let me open this, and here you can see that in pop-I position we have 8 values, 1 2 3 4. So our first 4 values, which will represent our distributed generation locations, are come from this function, hill function, and that is local search. And this is the way how local search is going to give us the possibility or variation in the distributed generation locations. And for the next 4 numbers, 1 2 3 4, that are randomly generated, and these randomly generated numbers then in further steps will be optimized by the ABC, I mean 2 19 30 23. So in this way ABC and LS will work combined to give us proper results. So let me click on the step button. Okay, so just a moment. So here when I click on the step button, so for next iteration, here you can see that nothing is fixed here. For every iteration it is going to change its values. 28 14 9 12 first 4 values are outcoming from the HLL, and HLL is here represent the 4 values, and random SRC and next portion, this one will represent the next 4 values. So in our next step, uh, in without distributed generation and with dg, we have a file that file name have a feed power. So by the feed power we are uh, in feed power we have 8 lines which representing the distributed generation. So here is the feed power, and this file is totally 100% exactly same to the without dg case, uh, but these lines, only these lines, only these lines are different from without digi case. So what is going on here? So here you can see that in ABC we have power factor, number of DGs, and N bus, that is 33, and pop-I position, that is our input for the feed power, and pop-I position have 8 numbers here. Here you can see here in this position. So here DATAIN represent that 4 numbers which are going to represent the first 4 represent location, and next 4 represent the distributed generation size. So here if unfortunately some uh, minus value come, then absolute will make it positive, because we have to. And then this is the calculation for the locations. Okay, and next here it is the calculation. Here is the 10 raised to power 4 d8 and 5 to 8 is representing the distributed generation size. So converting it into per unit and converting into a real and reactive. Here is the lines for real and reactive conversion. So here is the point where dg is working. So if we have a dg at 11 position, then at k3 will be 11, and at 11 position we have to store 2 value 2 of the distributed generation, and that is actually 2 value. And next we have to, at 19 location we have to store 19, that is the distributed generation without per unit. So here all the uh, 4 variables of distributed generation size and locations will store here, and then all the algorithm will go there, and it will be calculate the power losses, and it will be calculate the. And here feed power have FOUT, out is its output, and here we have FOUT, that is F1 VAL, and F1 VAL, what is it? Is sum of real power. So our output is the real power losses. So that real power losses are coming to pop I cost, I mean which we have pop variable here, and its cost value here represent the distributed generation power losses. So this is our main constraint here. So let me click the debugger here and remove these debuggers. Let me click on the continue button. Then here we have 100 different combinations. And what are these 100? This 100 is our n population. So for different 100 populations we have 100 variations, 2.4916, 2.4283, and all these variables. And here you can see that from these lines I have put the best value into the best solution. So let me open the best solution. So what will do the best solution here? Best solution will store the best pattern from here, and first it will choose the minimum value from all these numbers, and then it will save accordingly. I mean, let's example, here is the, let me open best solution 2.3967. so let me search where is this number. So for example, here is 2.39 is the best value, here is this number. So it will store the combination also, this combination will be stored into best solution. So next we have to go into further, and here is the step, and there is the main ABC loop started, and here is the formulation for the ABC calculation. And here let me click on the debugger here. When I click on the continue button, then here again we have heal function. Let me click on the step button. So here you can see that 11, 19, 14, 16 was our first attempt from the hill climbing. So when I click on the step, now check me, HLL is 29, 17, 29, 6. So here is 11, 19, 14, 16. So what I want to explain is that for every next attempt or next iteration, the hill climbing local search will generate a different number. That's why when you run this program for multi times and many times, our output will be a little bit changed. So this will be represent the first 4 numbers from the hill function, and that represent the distributed generation locations, and next 4 numbers from newbie position, and here is newbie positions, and these numbers will represent the distributed generation size. So let me click on the step, and now check me newbie position. Let me open this for we have 3 types of bees. So we have here bees, and initially we have set randomly numbers, and now we are going to this set was actually randomized selection, not this is not a part of the ABC. This is the randomized selection. So here we have a ABC part, and here we have newbie position. Let me open the newbie position from variables. Here is the newbie position, and again first four numbers 1 2 3 4 numbers represent the digi location, and next four will represent the digi size. So later on we will fix these numbers, these four digits, into by ABC into real numbers, because we have from 1 to 33 we have exactly numbers 3 4 7 on which bus we have to install. So here we have a step button, and newbie cost will calculate the cost for this. Then again we will here comparing this cost, newbie cost, with the uh, cost that we get from the pop function. So here is the all these, so we will compare this, and we will store the best pattern into pop I. I mean, we are going to overlap the existing value. Firstly, initially we have done pop I, then we have done here newbie, and best value will be stored in newbie, and then we are going to compare, and we are going to overlap into the pop I. So let me click here, click on the continue button, like click on the step button. Here is the next part, that is on locker bees. So let's click on the debugger here, and click on the continue button, click on the step, step, here again step, here again hill function is going to start, and let me open the cursor here, and 722 11 for every iteration, for every number. Hill climbing is here in this program ABC to provide the best combination for the distributed generation locations. So nothing is fixed here, that is done by the optimization. So let me click on the step button. Here it will be cost, the again newbie cost. And what is newbie cost? Here is newbie cost is, you can see here in 2 point, in the second row 2.6485. Again in this step it will be overlap from newbie into pop I. From above we have done into newbie into pop I. From here we are going to overlap newbie into pop I functions variables. So in this way, at the end, best variable value is stored in the best solution dot cost. So here best solution, I mean, just open the best solution. Here you can see that our best solution have 8 numbers. First 4 when we have actually we are doing this when we have 4 digits. 1 to 4 will represent dg locations, and 5 to 8 represent the dg size, first 4 locations. And then we have to we are going to run the load flow analysis again by the best solution position, which we have get from here. From these numbers we have actually this for the first digit, this for the second, third, and this for the fourth digit. So here we are going to run the feed forward again with the best possible values, and then we have to load the what is this resg.mat, open the feed forward, and here we stored the best results, I mean power loss, reactive V stability, and here is the power, I mean voltage profile comparison. So let me send you these updated files to you, and I hope so just you have to explain these things there, and that will be fine.